Okay, so in 4.3, talking about some of the different rules we have for taking derivatives. All of these things in this section are designed to speed up the process when we take derivatives of functions, right? We've learned our limit definition of the derivative, and our limit definition is helpful just because it helps us kind of see where this is coming from, but it's cumbersome, right? It's a lot of work. It's pretty dense to simplify. So instead of using this, we're going to focus instead on some tricks that we can use to help speed up the process, right? This section is essential because it saves us the time from having to use the limit definition every single time we need to take a derivative. If this were a full calculus course or just a slower paced class at all, we would actually go through all of these and prove them with the limit definition to show you how they came about. But that's not the purpose of this class. The purpose of this class is just to give you the essentials and the tricks that we can use to make our lives easier. So we have the power rule, which we've already talked about a little bit, right? I hinted at it in 4.2. And the power rule says this. The power rule says that the derivative with respect to x, so that's all that notation means, of x to some power, and of course I said here that that power is a real number. All I'm going to do is I'm going to take that exponent, move it down front as a coefficient, and then lower my existing power by 1. So that power n is going to come down, right? N is going to come down as a coefficient, and then I'm going to lower that power by 1. So this is the notation that I'll use kind of throughout this section. This d by dx, this other derivative notation that I hinted at earlier in the chapter. Just because it makes it easier to write some of the things we'll be talking about, but if I were to express this using my f prime notation that we used last chapter, or sorry, last section, I could say this: if f of x is x to the n, then f prime of x, the derivative of x, is nx to the n minus 1. So that's all we have going on here. Well, I can do a couple things by extension based on what I have here. The first, kind of just my smaller case here, is to say that the derivative of x on its own, well, this is x to the first, right? So that 1 is going to come down in front. I lower the power, I get x to the 0, which is also just 1. So the derivative of x on its own is just 1. I could say that the derivative then of a constant times x is just that constant. This is a base version of a generalization to say that the derivative of a constant times any function is the same as saying that constant times the derivative of the function. So I can move that constant outside my derivative. I can deal with the function on its own and just tack the coefficient on later. So that's all that's saying. And of course, in all of these, c is a constant. Oh, one more thing. The derivative of just a constant on its own is 0, right? Because if I consider the graph of a constant, there it is, that whole graph is a horizontal line. A horizontal line has 0 slope. And of course, derivative is a measure of slope. So if the if the slope is 0, so is the derivative. So a whole bunch of rules just to kind of get going. A lot of things that will come back throughout the rest of this section. So some examples. If f of x is x to the 4th, and I take the derivative, like I said, that power is going to come down as a coefficient, and I'm going to lower the power by 1, so 4x cubed. Same thing here with g of x, except I have this coefficient that I'll deal with later, right? So it's just 3 times the derivative of g, and I'm just going to use my power rule. So power comes down, power gets lowered by 1, simplify, 3 times 5 is 15, 15x to the 4th. H and v don't look like they're necessarily functions, powers, but they are. I could rewrite these as powers, so I can say, instead of 2 divided by x squared, I could say 2x to the negative 2. In that case, I have a power, and I can just use my power rule, so I have a coefficient. I'll deal with that later. But otherwise, this is 2 times the derivative of x to the negative 2, so I'll bring my power down, and then lower the power by 1. multiply to simplify. Negative 4x to the negative third. And in some cases, you may want to consider actually rewriting it as a rational expression. But either one of those is fine to me. I find the exponents easier to deal with in calculus and the fractions easier to deal with when I'm doing anything algebraic. So something to consider. It's the same idea with v. I can take v and rewrite this as a power as well. If I square root, I have a rational power, and that's just x to the 1/2. So now I have a power. I can use my power rule. I have another coefficient that I need to deal with, so I'll hold off on that. Same thing, power comes down, power gets lowered by 1, so I have negative 1/2 there. Simplify this, I have, maybe if I want to write this as a rational expression, I have 2x to the 1/2 on the denominator, so I have 3 over 2 root x as my derivative. So a little bit of algebraic manipulation, a little bit of just playing with it every so often. But it all starts with just that simple rule, right? Power comes down as a coefficient, so it gets multiplied onto any existing coefficient, and then you lower the power by 1. If we extend this out to more than one term, right, if I want to make my functions more interesting, I have a sum and difference. So in the same way that the limit of a sum or difference, right, the limit of a sum or difference is equal to the sum or difference of the limits, the same thing is true with derivatives. So if you notice here, I kind of go term by term. I'm going to do the same thing, maybe I'll use a different color, with derivatives. So I'm taking the derivative of a sum or difference of functions, and I just go term by term. So I want f prime of x plus or minus g prime of x. So just for the sake of introducing a notation I'm going to use later, if I let u and v be functions, so now I'm just going to consider u and v to be functions, then I would just say u prime plus or minus v prime. This is just a notation we'll use later on. These are functions. But just for introducing it now, I just want to kind of show it. All I'm doing, the big idea, is that I'm just going term by term. So for some examples, one term at a time. So my first example here, I have 3x to the 5th plus 4x squared minus 5x plus 3. So take this one term at a time. I have a constant here, so I'll leave that out front, times the derivative of x to the 5th. Well, this is just a power, right? So power comes down, lower the exponent by 1. Use my power rule. Same idea for the second term. Deal with that coefficient later. Power comes down, lower by 1. Same thing over here. So here's my coefficient. Remember that there's a 1 hiding up here, right? And we said that the derivative, where'd it go? There it is. The derivative of just x is 1, so it effectively, I guess, just disappears and leaves the coefficient behind. And then, as we said, the derivative of a constant is 0, so this just totally disappears. Right, derivative here of a constant is 0. Simplify a little bit, so my derivative is 15x to the 4th plus 8x minus 5. It's the same idea with g of x, but I've got this rational expression right here that I can rewrite as a power. So my first step actually should be to write this in terms of all power. So everything is expressed as a power. So instead of 1 over x, I have x to the negative 1. So I'll just take the derivative. Power rule again, so 2 times whatever my derivative of x cubed is, which will be 3x squared, and then same idea, power comes down, lower the power by 1, so this is 6x squared minus x to the negative 2. This is acceptable as a final answer to me. Like I said, in calculus, I prefer just to leave everything as a power when I can. But if you would prefer to write it this way, you're more than welcome to. It's all algebraically the same. So it was a really quick overview of just power rule. So power rule, what to do with the sum and difference, so just going term by term, and some examples of that. The next rule, and kind of the rule for the rest of the section, get a little bit dense and can be a little bit tricky if you're not careful. It's not the color I want to use. I want to use black. So the product rule, right? We've talked about adding and subtracting functions. Now we want to talk about what happens when we multiply them together. So what happens when I take the derivative of the product of two functions? And I'm going to call those functions u and v. And the color coding, I think, is really, really helpful here. So if I have a product of these functions, I can't just kind of, so to speak, distribute the derivative, right? I can't just do u prime v prime. That's not how this works. We actually have a rule for this. So we're going to derive the first term and leave the second one alone. But we're not done yet because v needs to get derived too. So everybody's going to get a turn. So this time I'm going to leave the first one alone and derive the second. So if you've noticed here, right, if I have u times v, I've got the first function and the second function. I derive the first, leave the second, then leave the first one and derive the second. So everybody gets a turn to be derived. And then because multiplication is just repeated addition, I have addition here. And so the trick that I like to remember, maybe something that would be helpful, every function gets a turn, right? I've been kind of saying this a lot now. Every function gets a turn to be derived, but I can only derive one function at a time, which is why I have these separate terms stacked up. So there's my product rule. So if I look at some examples, u prime v plus uv prime. Here's a product. I could just FOIL this out, but I don't need to because I have a rule that lets me work with a product. So let's kind of color code here. One of the things I like to do all the time is I like to do a lot of side work with these problems. So the first thing I'm going to do is identify my u and my v. So I think it's really important to do this side work here to keep everything organized. It's really important to stay organized with this work. The neater you can be, the easier it will be for you to keep track of all of kind of the moving parts of these problems. So I've got my u and my v, and I know, maybe I don't want to go to color yet, if I look at the derivative of this function, the rule is u prime v plus u v prime. So I have a u and a v, but I need a u prime and a v prime, so I need to find that. So I'm going to derive the first function. Well, the derivative of x is 1, and the derivative of a constant is 0, so my u prime is just 1. And then my v prime, is the derivative of v. So power rule, I'm going to bring the exponent down, lower the power by 1, so I get 2x plus 2. So there I have all 4 of my parts now. And some teachers actually like to teach this as almost like if you set this box up like this, almost a kind of cross multiplication, right? If you follow my rule here, you see u v prime and v u prime. So if that's something that helps, you can absolutely think about it that way. I just have this rule ingrained into my head, right? I just kind of have this, after years and years of doing this, just kind of stuck into my head to do it that way. So whatever method works, if you like to think about the cross multiplication, that's absolutely fine. Whatever helps you remember it. The good thing about doing all the side work is now I have all the pieces I can just plug in. So u prime is 1, and even though it's just a 1, I'm going to plug it in just so I remember that I've done it. V is x squared plus 2x minus 1. And then I have u is x plus 2. And then v prime is 2x plus 2. And I want to simplify that, so I'll just do my distribution. Be careful when you FOIL, so 2x squared plus 2x plus 4x plus 4. And just to simplify one last time, I have 3x squared plus 8x plus 3. And I can leave it just like that. This is the derivative of my product, and if you don't believe me, you can FOIL out the original function and derive that using the power rule, and you'll get the same exact thing, but I'm not going to do that here. So what are some of the key takeaways here? What are some of the key tips here? The biggest one, side work. It's really helpful to isolate your information, just like I did over here. Isolate and pull out your u, pull out your v, and I know I need the derivatives of both of those functions, so I'm going to find those. The other big tip is to work neatly. Right, the neater I work, the more organized my work is, the more it'll stand out. Let's highlight this box. Not only the more it'll stand out, but the easier it'll be for you to find the information that you're looking for, so that you can plug everything in the way it needs to be plugged in. So your two big tips in these problems and kind of throughout this section. Side work, always do some of this side work here to stay organized. And on the topic of organization, keep your work neat. So let's try another one. So I have a product again, right? I have 2x cubed plus 4x squared minus 1, multiplying that by x to the 4th plus 5. So same thing, I'm going to identify and then isolate my u and my v. I'm actually going to write them in u and v. And now I'm just going to do some work in the margins. I'm going to do some work off to the side first. So I have u, and I know I need its derivative, so we'll find u prime, and u prime is going to be 6x squared plus 8x. Likewise for v, I'm going to do the same thing. And the derivative is just 4x cubed. So now that I have all my pieces, I can go ahead and deal with my actual product rule. I really like to write out my product rule or any general formula I'm using. I like to write that out in full, completely in full, so that way I know immediately, instantly what to plug in where. Right? There's no confusion about it here. If I look right here, everything is spelled out right for me. I know I need to plug in each of the parts I'm stating and where. So I'm not skipping steps here. So plug in u prime, plug in v, plug in u, plug in v, and simplify. So FOIL a lot, 6x to the 6th plus 30x squared plus 8x to the 5th plus 40x. And then over here, I'm going to get 8x to the 6th plus 16x to the 5th minus 4x cubed. A little more work, 14x to the 6th 16x to the fifth. Nope, sorry. 24x to the fifth. I have no x to the fourth. Minus 4x cubed. Plus 30x squared. Minus 40x. I think I got them all. So there's my derivative right there. And once again, if you're a little bit unsure and you want to check this for sure, you can absolutely go through and derive everything, FOIL everything, and then use the power rule. But this is meant to be a shortcut. This is meant to save us some work, save us some time.